next presenter is Keya, and she has a schedule conflict, so I will try to show her slide, but I cannot compete and present it as a solid talk. I will just focus on a couple of important things, and everyone is welcome to cooperate and be author, so it will be like not only Keya, but the whole club of computational chemists. So, as we have heard from Joseph, it is quite beneficial to follow Sarah and compute photoluminescence spectrum. Those are based on our previous calculations of non-radiative relaxational dynamics. This is important. This is different from absorption spectra because the non-Kasha transitions may involve transitions between excited states. And in order to activate them, we need to populate orbitals that are not populated in the ground state. So we need to explore excited state dynamics as a prerequisite to compute photoluminescence. So one has, well, we all have a little code on the top of the quantum dynamics that just converts these dynamics into photoluminescence spectrum. And the aspect that Case was going to show, and I'll just surface her proxy, is just to focus on a couple of lines of the code that are responsible for this emission spectrum. So here the standard things and the name of the code. I hope very much that next few speakers will cover these aspects in more details and from different points of view. So one of the important things that is needed for computing spectra is to import this 4-master optics file, which to my understanding contains oscillator strengths for all possible pairs of orbitals, including both from occupied to unoccupied, as well as occupied to occupied and unoccupied to unoccupied. And I believe on one of the previous talks, previous weeks, David was giving comment about structure and location of this file. So upon the dynamics is done, the data for occupations of the orbitals in the valence band and conduction band need to be merged with oscillator strengths in the right way. So here are a couple of lines of the code that do implement the equation on the top. So there were a lot of very important key concepts that Joseph has and contributed to us. But there is one keyword that was implicit but not verbalized. When William was showing his diagrams with little levels, dots, and wavy lines, there was naturally assumed that emission happens from excited to ground, when population goes from higher energy level to lower energy level. If we believe in Boltzmann distribution, if we believe in thermodynamics and thermodynamic equilibrium, this should never happen. All occupations should go to the ground state, right? So the prerequisite for emission is in conflict with equilibrium thermodynamics. It should be a non-equilibrium state. So in a regular, stable thermodynamic equilibrium state, we populations are falling. What's the right word for freshman chemistry? When all Fermi Pauli exclusion principle, up to Fermi level, everything is occupied, above everything is empty. Right? And now we need to violate this rule. We need to promote an electron higher up. We need to have a non-equilibrium. We need to have populations that are opposite to this natural arrangement of things. So it should be inverted. And the keyword is population inversion. The prerequisite for photoluminescence is population inversion. And we may set up scanning of the pairs of orbitals in such way so that we have one is always more senior than the other, to know who is senior, who is junior between orbitals. And then we can look if we ever have population, so let's look on the green box, if you have population of the higher orbital bigger than population of the lower orbital. So if the subtraction is positive, it means we observe population inversion. If it is negative, then well, we already arrange summation in such way that it will not be negative. We count on the possible contributions. So this little box bracket is population inversion. Okay, another prerequisite for photoluminescence is that it should match the emitted photon matching energy difference between initial and final states. So the frequency of emitted photon is equals to energy difference between initial and final. And the third prerequisite is that emitting pair of states should have non-zero oscillator strength, should have non-zero transition dipole, and should be able to contribute. And then we scan over all the things. So populations are time dependent. Therefore, as we run through quantum dynamics, there are different pairs of orbitals that contribute or not contribute to the emission. And in this slide code, we have time dependent populations. We have the energy differences, and we have the oscillator strength that depends on two indices. When all these factors are combined, just basically multiplied, we implement resonance condition. Instead of delta function, we have Gaussian function, exponential, and the scanning over all possible emission frequencies is arranged as a contribution over all possible transitions is arranged as summation of different terms of this thing. So the resulting variable slice is a probability to emit a quantum at certain wavelengths at certain time. And if we scan through all possible time steps of our quantum dynamics, we will see that at each time slice, these probabilities as function of frequency are different. Right? So if we accumulate data into this array by adding more and more rows each time it comes through the cycle, it will be a matrix. And we'll forward to be a little less abstract, more practical. So the emission for certain systems can be even more pronounced of these non-Kasha transitions. You will get the Dinesh was asking. But the experiments that track time dependence of emission are cool and needed, but they are 10, 100 times more expensive. Much more typical ways to look on just whether it emits or not. So calorimeters are much like one can even buy it into a household. It's not more expensive than an average car. So one can integrate all these emission events over timeline and have this integrated emission. Let's go back to the line of code. So we do have this emission thing. One could make just summation along each line of this matrix, but since we have the time steps have different duration, one needs to arrange the varying increment of time into this integration. But as soon as this little convolution of two matrices is done, you have time-dependent emission. Another thing which is often shown doesn't have any relation to practical observables, but it does appeal to intuitive human thinking. So if we forget about this strange things about from non-crusher emission, below gap emission, and just follow how the excited state of different energy cascading from more excited to lower excited, we can model this process just by arranging this population of electrons, population of flows, and the resonance condition, and just illustrate so that initial excitation at certain wavelengths, certain energy changes over time and drops to the form of dynamics of excited state. Again, it is not an experimental observable. It is not anything we compare. It's only a way to interpret how things are arranged. Okay. And practically, while studying certain materials, we may want to redo this calculation again and again with different initial conditions, because the emission properties do depend on excitation energy. Let's see if here shows here things together. Okay. The presentation is done. You can skip upload since the presenter is not on the meeting. But any questions, please go ahead and ask questions, and I'll either try to address them or we will postpone until he joins us next meeting and answer more questions. Yes,
just say one more time on this slide, I guess, what the P is.
This one that is right now,
like what it all is. Is that like the power, the intensity?
Well, but P is here for excited state to appear at certain transition energy at a certain time. So in the code, it is encoded based on the name of one of my postdoctoral advisors. Either, I don't know, as a making fun of him or as a making tribute to him.